Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on February 16, 2026, just yesterday. It introduces a database system that treats quantum computation as a first-class execution option, effectively compiling SQL queries into quantum circuits to outperform classical methods on a real 72-qubit processor. The paper is titled Qute, Towards Quantum Native Database, and as we'll see later, the results for large-scale data filtering are really impressive. And for those interested in the implementation, the authors have shared their code on GitHub. So, Figure 1 outlines the three-stage evolutionary path the authors envisioned for this technology. First, on the left, we see the quantum-assisted stage, where the quantum chip acts largely as a coprocessor for specific tasks like filtering, while the main data stays in classical storage. In the middle, the quantum-centric stage, which is where the Qute system fits, introduces hybrid storage and a smart optimizer to balance workloads between classical and quantum hardware. Finally, the vision concludes on the right with the quantum native stage, featuring unified quantum memory capable of handling complex multimodal analytics entirely within the quantum domain. So to realize the quantum-centric stage we just saw, the underlying architecture must evolve significantly, which Table 1 details. For the compiler and operator layers, the system moves away from generating machine code for tuple-at-a-time processing. Instead, it generates circuits that utilize amplitude and interference operations to process data directly on the back end. The plan optimizer also faces a new challenge. It cannot just solve for deterministic costs. It has to dynamically trade off potential speedups against the noise and success rates inherent to quantum hardware. Finally, data indexing changes its role from simple acceleration to actively shrinking the dataset, ensuring the candidate set is small enough to load onto the quantum processor. Alright, Figure 2 presents the complete system architecture required to make that vision a reality. At the top left, the query engine takes standard SQL and compiles it into quantum circuits using a three-level intermediate representation. This feeds into the query optimizer, which employs a fidelity-aware cost model to dynamically trade off latency against success probability. To the right, the execution engine runs these plans using specialized quantum operators, such as Grover for filtering, alongside quantum-aware indexing to reduce the data load. Finally, the storage engine at the bottom supports the whole stack by managing data durability and refreshing noisy quantum states. So with the architecture in place, Table 2 details the specific instruction set the system uses. It maps standard SQL operators, like filtering, joins, and aggregations, to their quantum equivalents. For filtering tasks like equality or range checks, the system employs variants of Grover's algorithm. You can see in the complexity columns that this offers a quadratic speedup, reducing the workload from linear time, or big O of n, down to big O of the square root of n. Moving to aggregations like sum or average, it uses amplitude estimation. Here the complexity shifts to depend on the desired precision, epsilon, rather than just the row count, allowing for fast, approximate answers on massive datasets. Well, Figure 5 takes those theoretical complexities and plots them against performance. The vertical axis tracks time in milliseconds, while the horizontal axis shows data scale, where n equals 2 to the power of k. On the bottom left, the green squares represent real runs on the 72-qubit processor, confirming the cost model's accuracy for small datasets. Moving right, we hit a crossover point marked by the star at roughly 2 to the 30th power. Before this, the classical database in orange is faster, but after the crossover, the blue Qute line stays much flatter, proving its advantage for massive workloads. Wrapping up, two takeaways stand out. First, Qute moves us beyond simulation by running compiled SQL on real quantum hardware. Second, the crossover at massive scales proves that quantum parallelism can genuinely beat classical linear scans for unindexed data. This paves the way for hybrid systems, where quantum processors handle the heaviest analytical loads. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.